In the last class we are discussing about the electrophoretic separation method, and this method becomes very important whenever we are talking about the separation of charged molecules are concerned. Now, most of the this has a relevance in case of separation and purification and analysis of biomolecules, because most of the biomolecules are charged in nature. We have seen that this particular property or charged property of the biomolecules will be depending on its pH. There is most of the biomolecules will be having a particular pH where the molecule is chargeless or neutral. This particular pH is called isoelectric pH. Now, various different biomolecules will be having different values of isoelectric pH. Now, if you use the operating pH different than from the isoelectric pH, the biomolecules will be charged according to your wish. Now, if you set your operating pH less than the isoelectric point, the molecule will be positively charged. If you set your operating pH above the isoelectric point, the molecule will be negatively charged. Now, in presence of an external electric field, if these molecules if these molecules are placed in a solution, preferably in an electrolytic solution, then and apply an external electric field, then these molecules will be moving to a particular electrode depending on its charge. So, therefore, if you set an operating pH such that a mixture will be having a mixture of let us say 4 components, let us say 2 of them will be having positively charged, 2 of them will be negatively charged at a particular pH, then if you apply an external electric field, the electrophoresis takes place and 2 molecules will be moving to one particular electrode and the other 2 molecules will be moving to the other electrode with opposite polarity. So, therefore, a mixture can be separated out by using this particular method, and the basic electrokinetic phenomena that is involved or responsible for this separation process is electrophoresis. So, electrophoretic separation method has become very important nowadays in order to separate the charged molecules. Now, this electrophoretic separation method can be utilized for fractionation purpose, for analysis purpose and things like that. Now, there are in the last class we also discussed some of the problems associated with the electrophoretic separation process. The major problem that will be arising out of it is the Joule heating. Because of the presence of external electric field, that means the external electric field will be created if you apply a voltage difference between the 2 points of the cell, then voltage difference divided by length will be the electric field strength. Now, because of the presence of electrolyte in the solution, there will be formation of electric double layer and the redistribution of the charges, coions and counterions and formation of electric double layer. This double layer will result into free or excess charges. Those will be moving under the influence of external electric field producing a current. This current can be causing a Joule type of heating like I square R. Now, this Joule type of heating is very deleterious or harmful in as far as the electrophoretic separation is concerned, because it causes the local temperature fluctuation that will lead to fluctuation in the density that will give rise to the buoyant force. If the buoyant force is more than the viscous force, then this will cause a natural circulation like natural convection sort of thing. So, the electrophoretic movement or the electrophoresis will be hampered. So, this is not desired. Secondly, at higher temperature, the protein molecules may be denatured. So, under all circumstances, this thing has to be subdued, has to be prevented. In order to prevent Joule heating and buoyant effect, generally a medium is placed into the solution, that is called either it is a gel or a membrane or paper. So, it is called gel electrophoresis or paper or membrane electrophoresis. Now, in order to prevent, now let us look into the various aspects of that. So, gel or membrane electrophoresis. this is done to prevent the natural convection or natural circulation in the system. Natural circulation like free convection. Okay. And a porous media, either it is a gel in the form of a gel or a membrane, is placed, and this method is known as zone electrophoresis. Okay. When you conduct the electrophoresis in presence of the gel or membrane, this is known as zonal electrophoresis. And the system behaves exactly like chromatographic column. Okay. And therefore, this stabilizing agent or the gel that you are going to use into the system, they must be having some desired properties. Now, let us tabulate these desired properties of the desired characteristics of the media, stabilizing media. Number 1, it should be inert and should not react with the existing species, those need to be separated. Should be inert and should not react with species. Secondly, no residual charges on the media should not be there. No residual charges on the medium should be there. This basically occurs, this is basically another problem that crops up during electrophoresis. This is because of the electro osmosis flow. Now, if we know that if you have a solution of the electrolytes and then you have a charged wall, now if you apply an external electric field, then the excess charges that is present, they will move under the external electric field in a particular direction, giving rise to another electrokinetic phenomena, that is electro osmosis. Okay. So, electroosmotic flow or the electroosmotic velocity will be added to the electrophoretic velocity in that case, and the separation will be marred. Okay. The separation will be obstacled. Okay. So, we would like to minimize two problems, one is the natural convection, another is the electroosmotic flow. So, no residual charges on the medium is desired in order to minimize the electroosmotic flow. Thirdly, the pore size should be greater than the molecular size, so that no hindered transport occurs. Pore size of gel should be larger than molecular size of the species. Why this is required? To prevent hindered diffusion. So, diffusion should be spontaneous and it should go unhindered. Okay. Now, we will just draw a typical schematic of laboratory gel electrophoresis cell. Okay, this is the solution and this is the main cell, and in between the gel is trapped. So, this is the gel and there is a sample port here. The bottom is there is a cooling plate in order to cool the system to prevent the joule heating. You cannot avoid the joule heating, you can minimize it. Then there is another bath. So, and this will be given to the cathode and this will be going to the anode. The whole thing is kept under a cover. Okay. Now, the salient features of this laboratory scale setup is that a thin layer of gel is polymerized onto the support plate, which is typically a glass plate. A thin polymeric layer, which is basically gel is glued. Glued means it is polymerized. Okay. It is polymerized on the base plate. Onto the support plate, which is typically a glass plate. Okay. Support plate is placed on a coolant plate, so that the joule heating is prevented. We have a coolant plate on which support plate is placed to prevent the joule heating. Gel layer should be about 5 millimeter for better heat dissipation. That is a typical dimension. Is about 5 mm for better heat dissipation, and the cover must be there in order to control some amount of evaporation and safety related issues during application of high voltage. So, generally the whole thing is kept under a cover. If there is some evaporation takes place at joule heating, there will be a temperature will be more, and to prevent the evaporation, and suppose you are using the high voltage, in order to have the safety in your whole apparatus, the whole apparatus is placed in a cover. Now, what is the operation? Let us look into the salient features of the operation. The first one is the sample is placed in the sample cell. Sample is placed in sample oil, that is called sample oil, at the center of the glass slab. When current is on, that means when the voltage is applied, solute of appropriate polarity will go to the migrate to the electrode of opposite polarity. On application of electric field, solute migrate to an electrode of opposite polarity. Okay. Now, if you have more than one species, this solute migration velocity will be that means the electrophoretic velocity will be different, because each of them will be carrying different charges, right. So, in a mixture species have different charges, maybe of opposite signs also, even in the same sign they will be having different values. Because of this, the electrophoretic mobility will be different for this species. Mobility differs for this species, and on the application of external electric field, the electrophoretic, since the electrophoretic mobility is defined as the electrophoretic velocity per unit field strength. So, on application of electric potential difference, then this electrophoretic velocity of various species will be different, and they will migrate at different velocities after some time. Okay. So, at the end of the residence time, different at different regions different species will appear. Okay. The products are therefore detected by ultraviolet absorbance or refractive index. By using these products are detected, and they are connected to the concentration of various species, exactly like the chromatographic separation process. The most common electrophoresis is polyacrylamide gel electrophoresis or Page. Commonest electrophoresis is Page PAGE, that is polyacrylamide gel electrophoresis. Okay. And there are, let us look into the advantages of gel electrophoresis. Let us list down advantages of gel electrophoresis. This polyacrylamide gel is an excellent anti-convective gel. I am talking about this polyacrylamide gel. This gel is a good anti-convective gel. That means, the gel structure is such that the convection is not allowed. Okay. So, it is basically subdued. Secondly, it is easy to polymerize in place. Polymerize in situ, in the same place. Third one is that it can be polymerized in the variety of pore sizes. It can be polymerized and the fourth one is there is little residual charge there is present on the polymer. charge on polymer, this simply allows the minimization of electroosmotic flow. This minimizes electroosmotic flow. So, these are the various advantages of Page or polyacrylamide gel electrophoresis. There is another Page that is quite common in use, that is called Sds Page. Okay. So, in this case a protein, when a protein solution at pH 7 is treated with 1% SDS, that is sodium dodecyl sulphate. This is a surfactant, this is an anionic surfactant. Sodium dodecyl sulphate and 0.1 molar mercaptoethanol, the polypeptide chain is unfolded. The polypeptide chain present in the protein is unfolded, and what it results, the protein molecule, this results into the protein molecule gets converted to a rod like structure. Protein molecule becomes a rod like structure. About 1.4 gram SDS is bound generally to 1 gram of protein to make a complex. For complex formation, and for each protein the attachment occurs in the same ratio, and surprisingly for each protein the complex is formed in the same ratio. So, therefore, the protein SDS complex have the same charge to mass ratio. Therefore, since the all complexes, therefore, the all complexes have similar electrophoretic mobility, in free solution, and they have but they have the different sizes. And this different sized complex then can be sieved or separated by the polyacrylamide gel. Different sized complexes are sieved or filtered, or they can be separated using by the polyacrylamide gel. Okay. So, this is the basic principle, and since SDS Page the value of electrophoretic mobility does not play an important role, only the molecular weight and the size of the species plays a very important role. This method is very useful, extremely useful in determining the relative mass of the protein, extremely useful to estimate relative mass of the protein solution, protein particles. Okay. Then let us talk about the zonal electrophoresis and how to quantify them. It is just exactly like chromatographic column. A pulse of the feed results a Gaussian distribution response at the exit of the setup. A pulse of the feed, it results a Gaussian distribution of response at the exit of the setup. What is the distribution? The distribution is like just like Gaussian expression. It will be something like this: C I is C max of the component I exponential minus Z minus Z I square of that divided by 2 sigma 1 I square. Okay. Sigma 1 I is nothing but the standard deviation of the response. Okay. If this is the Gaussian distribution at the exit, then the width is basically the standard deviation, and Z I is the location of maximum peak, location of maximum peak. Now, we can quantify the various quantities those are involved in the calculation. The total electrophoretic velocity is nothing but a sum of electrophoretic velocity plus electroosmotic velocity, that is the net electrophoretic velocity. Velocity is given as V net. This will be nothing but mu times E plus mu OSM times E. What is mu? Mu is nothing but the electrophoretic mobility. So, electrophoretic mobility is nothing but velocity per unit field strength. So, electrophoretic mobility multiplied by the electric field strength, that will be giving you the electrophoretic velocity. Similarly, mu OSM is nothing but the electrophoretic mobility due to electro osmosis. And what is E? E is the field strength. This is nothing but the potential difference that is applied between the 2 points divided by L. L is the length of the setup. Okay. V is the electric potential applied between 2 points. That means, if I am having a cell something like this, let us say this is positively charged, this is negatively charged, and this will be and you just apply an external electric volt of voltage V between the 2 points. One is the cathode, another is the anode, and this length is L. Then the electric field strength is given by V by L. Okay, and V is the you must be having some external electric power supply, either a battery or some voltage supply, external voltage supplier. So, V by L is given by the electric field strength. Therefore, the expression of Z I or the location, and L is the, so what is L? L is the maximum length of migration. If Tr is the average retention time to migrate a distance Zi. Tr is average retention time to migrate a distance Zi, then the expression of retention time becomes Zi divided by V net. Okay. The distance divided by the velocity. So, if we put the expression, so this becomes Zi and Vi, I just V net is I put mu plus mu OSM times E, and E I am going to substitute by V by L, because E is not the operating variable, directly direct operating variable is voltage, and length is known to you. So, it will be Zi times L divided by mu plus mu OSM times V. So, E is replaced by V by L. So, expression of Zi can be obtained as mu plus mu OSM V by L times Tr I. So, let us say Tr I is the retention time corresponding to ith component. So, Tr I is the retention time for ith component. Now, for say since the chromatographic run is for a fixed time, we have basically this retention time is nothing but the experimental time, and we know what is this value. This retention time is nothing but the experimental time. That means the Sds page is run for electrophoresis is run for, let us say 2 hours, then 2 hours will be nothing but the retention time. Okay. So, different particles will travel different distances because of the difference in electrophoretic mobilities. Okay. The width of the concentration curve. So, basically the concentration curve that I will be getting at the exit is given by the width is the sigma I. So, width of concentration curve is given by Einstein's equation. What is that equation? Sigma 1 I square is nothing but 2 times d effective I t experimental. T experimental is same as the retention time, and it will be basically an operating condition. You are going to run the system for 2 hours, 1.5 hours, 5 hours, something like that. And what is d effective I is nothing but the effective axial dispersion coefficient in the electrophoresis system. Coefficient. So, one can have the sigma 1 I square as 2 d effective Z I times L divided by mu I plus mu osmotic multiplied by V is the voltage. Okay. So, that is the basically the width of the concentration curve, and one can have if there are 2 components, 2 species present, one can have the degree of resolution, okay, how good they are separated. So, resolution R can be defined, resolution between the 2 zones can be defined, and this is defined as 1 by 4 V by L T E experimental divided by 2 D effective raised to the power half mu 1 minus mu 2. Okay. So, degree of resolution becomes very important, and your T experimental you already obtained as earlier. T experimental is nothing but L by V net. Okay. And what is D effective? D effective in a typical system is an arithmetic mean of the diffusivity of the two species those are present in the system, half of D1 plus D2. Now, based on this you can determine the what is the degree of resolution, okay, for these systems. Closer to the to be a 1, that means it will there the degree of resolution is very good. Now, with this theoretical background, I will be just solving couple of problems just to have an idea how these systems work and how to get down into the some numerical feelings of the system. Some example problems. Let us consider the first example talks about a batch electrophoresis system. Phoresis is done with Page, okay, with the system is so efficient that the electrophoretic mobility due to electro osmosis is 0, okay, and mu of A, there are two species present, A and B. The electrophoretic mobility for species 1 is given as 1.05 into 10 to the power minus 5 centimeter square volt per second, and mu of B is 1.033 into 10 to the power minus 5 centimeter square per volt second. Okay. Diffusivity of the two components are very close, and they will be equal for this particular example 1.5 into 10 to the power minus 7 centimeter square per second. Okay. So, if you look into the order of magnitude of diffusivity, they will correspond to 10 to the minus 11 meter square per second. They are typically diffusivity of the protein solution. Okay. And the electric field strength that we are going to apply here is 125 volt per centimeter, and we are applying it for 2.5 hours. Okay. So, we are applying this much of electric field strength of 125 volt per centimeter for 2.5 hours, and what we have to find out that we have to find out the location of the peak basically what is from the feed well, the location where we have injected the feed from that particular position, the peak widths and resolution. Okay. These quantities we have to find out. Now, just before going into looking into this thing, now let us just like to see a typical concentration plot at the exit of electrophoresis unit. Okay. This distance is basically the this is the location where the feed is being injected. So, this is concentration, and this is the location or distance, this is 0 location. Now, suppose you will be having the anions and cations both are present. That means, you will be you are setting your operating pH such that some of the species will be positively charged, some of them are negatively charged. Okay. So, they will be attracted to the opposite polarity. Okay. So, let us say these are A1 and A2, and A1 A2 are the anions, and these are C1 C2 and they are the cations. Okay. They move in the opposite direction, and this is this distance between the the width of the concentration peak is given by 4 times sigma. Okay. And this is the location where the zero charge is present. Okay. So, this is the isoelectric point. Suppose you are setting an operating pH 4, and if you have some protein which is having a isoelectric point at 4, that will be staying here. And if for the other isoelectric point for the other proteins which will be having the other isoelectric points, depending on their polarity, they will move to the different electrodes, and this is the width of the concentration curve that we are talking about. Okay. Okay. Now, let us get down to the calculations. Z I is mu I E T E experimental. Mu I E is nothing but the electrophoretic velocity. So, for the protein A, the distance Z A is nothing but 1.05. You just put the values corresponding to protein A into 125 volts per centimeter into, it has been operated for 2.5 hours into 3600. This conversion factor is given for to convert hour into second, because the electrophoretic mobility is given in second. Yes, and this Z A turns out to be 11.81 centimeter. Okay. And Z B, correspondingly you can calculate 1.033 into 10 to the power minus 5 into 125, 2.5 into 3600, and this turns out to be 11.62 centimeter. So, these are the regions where the maximum peak of A and maximum peak of B will be occurring. Okay. Now, let us look into the width of the concentration curve. Sigma I square is given as 2 D effective times T experimental, and sigma, if you put the value of sigma I, then it turns out to be 0.052 centimeter for both proteins. And the width is nothing but 4 times sigma. Okay. That is the peak width 4 times sigma, and this will be 0.208 centimeter. Then you can look into the expression of resolution. The expression of resolution becomes 1 by 4 times E under root T for experimental duration divided by 2 D effective multiplied by mu 1 minus mu 2, and if you put the various values, this turns out to be 0.9202. Okay. Now, if you look into this, so that is the resolution we are talking about, and if you look into the expression of resolution, you can check, you can see that R increases more with the resolution, it will be better, right. R increases by increasing E. If you increase E, then R increases, and if you increase T experimental, it will increase. That means, if you conduct the experiment for longer duration, the resolution is supposed to increase. Okay. Then we will look into one more example. Here you will be having different values of diffusivities. Now, again we are talking about a batch electrophoresis. Done in Page. With osmotic mobility, electroosmotic mobility is 0, and the mobility of the two proteins are, again you are having two proteins A and B, and mobility of protein A is 10 to the power minus 5 centimeter square per volt per unit time, and that is for B is 1.02 into 10 to the power minus 5 centimeter square per unit volt per unit time. The diffusivities are dA is given as 1.5 into 10 to the power minus 7 centimeter square per second, and dB is 1.7 into 10 to the power minus 7 centimeter square per second. Okay. The experiment is conducted at the operating electric field is 100 volt per meter, and this is for 3 hours. This is 100 volt per centimeter, I guess. Okay. So, now we have to again find out the location of the peaks, peak width and the resolution of the two proteins as we have solved in the earlier problem. Okay. Now, the solution is almost the same thing like the earlier one. The migration distance can be obtained by putting the values there. Z A is mu A E T E experimental. So, mu A is given as 10 to the power minus 5 into 100 into 3 into 3600, that is for 3 hours. So, this distance is 10.8 centimeter. On the other hand, you can find out the migration distance for the protein B as mu B times E time for experimentation, that is 3 hours. So, you just put the values 1.02 into 10 to the power minus 5 times 100 into 3 into 3600. So, it turns out to be 11.02 centimeter. So, what does this mean? This means that location of peak for component A will be at 10.8 centimeter and the component and the location of the peak for component B will be at 11.02 centimeter. So, Z values, they represent the location of the peak at the exit of the system. Now, what you have to do? You have to calculate the effective diffusivity. The effective diffusivity will be dA plus dB divided by 2, and if you substitute the values, it turns out to be 1.6 into 10 to the power minus 7 centimeter square per second. Okay. So, you can find out the sigma square. Sigma square is nothing but 2 d effective multiplied by t experimental, and if you put the values, this turns out to be 2 into 1.6 into 10 to the power minus 7 into 3 into 3600, and this is 3.46 into 10 to the power minus 3 centimeter square, and sigma turns out to be 0.0587 centimeter. The width of the peak becomes 4 times sigma, and this is, if you just put the value, this value here, it turns out to be 0.235 centimeter. So, once you know the different parameters, you will be in a position to calculate the resolution of the peaks as well. So, resolution is 1 by 4 times E mu 1 minus mu 2 times under root T experimental divided by 2 times D effective. Now, you just put different values 1 by 4 into 100 into 1.02 minus 1 into 10 to the power minus 5 under root 3 into 3600 divided by 2 into 1.6 into 10 to the power minus 7, and this turns out to be around 0.92. The resolution is around 0.92, and R can be increased, as we have talked earlier, decided earlier, that by tuning the operating conditions. What are the operating conditions? The operating condition is electric field strength. That means, if you apply more voltage, then electric field strength will be higher. If you apply if you conduct the experiment for a larger duration, the duration of the experiments will be higher, and one can get, one can increase the resolution, and one can get a higher separation. So, this basically gives a demonstration of how electrophoretic separation process takes place, and if we summarize that, this is very important as far as the separation and analysis of the biomolecules are concerned, because of the charged properties of the biomolecules, and you must be having some pH. So, every biomolecules will be having its characteristic pI or isoelectric point, where the charge of that particular biomolecule will be neutral. Now, based on the operating pH, you can really set the you can tailor make the charge of the biomolecules. And now, if you apply an external electric field, then these biomolecules will proceed to various electrodes depending on their polarity. Now, this process, the electrophoresis, will be giving rise to several complications. Number one, that because of the presence of electrolytes in the solution, it will produce a current, and that current will give rise to Joule type of heating, which may degenerate the protein, or it may give rise to a natural circulation like natural convection, which will hamper the electrophoretic movement. So, one has to go for a gel type of medium or a porous medium, so that the effect of natural convection will be minimized. Number one. Number two is that the pores of the porous medium must be large enough, so that the diffusion of the species through them should not be hindered. And number three characteristic is that there should not be any electro-osmotic velocity, that has to be minimized, otherwise the whole thing will be marred and there will be no resolution you will be getting. And therefore, you must be having a gel which will be polymerized typically, so that the charge will be, the residual surface charge will be minimal, so that the zeta potential of that will be extremely small, and you will be having almost no electro-osmotic velocity. So, that more or less completes the electrophoretic separation method. So, in the next class I will stop here. In the next class we will move on to the next separation method, that will be the supercritical fluid extraction. Okay. Thank you.